We all know that the Tesla 4680 battery is currently the most advanced battery that Elon has for his Tesla EV. But speaking quite frankly, it can't be denied that it is not yet impressive enough to surpass potential batteries like Toyota and Volkswagen's solid-state batteries. However, that's going to change soon as Tesla's aiming for the 4680 battery Gen 3 with at least two crazy changes that'll make it the leading battery technology in terms of chemistry. Of course, if Tesla succeeds. So, let's get into what is this 4680 battery Gen 3 change. You may not know yet, but 4680 batteries has actually gone through two generations, initially in the Model Y, but it was not very efficient, so Tesla took it out to go back to using the 2170 and LFP. Right now, 4680 cells currently being made at Giga Texas are the second generation, which have a 10% higher energy density than what they use in Model Y. They're called Cybercell because they're mainly used for the production of Cybertruck, with a 123 kilowatt-hour battery pack size consisting of 1,344 battery cells. Although it does provide quite good performance, it's clearly not enough, and Elon realizes this is not the final destination of this battery technology. So some recent reports announced that Tesla will soon produce the next generation of the 4680 battery to form a complete version, and we call it Gen 3. If we say the 4680 Gen 3 battery will make the Cybertruck or any future model integrating it cheaper and more powerful, you might not believe it, but that's soon going to become a reality. Let's take a look at the first major change that makes it significantly cheaper. The 4680 Gen 3 battery utilizes Tesla's dry electrode coating process. 1. What is 4680 battery dry coating electrode, and why does the 4680 battery need the dry coating electrode? Okay, to recap, Tesla first introduced 4680 cells at Battery Day back in 2020, confidently stating that this type of battery would give 5 times the energy and increase the range by 16%. But it's not clear if it has yet reached that level of performance because Elon has not yet been able to uniformly apply dry coating to both the anode and cathode of the 4680. Until now, battery electrodes have mainly been coated using a process called the wet coating process. This process involves mixing a powder mixture of active materials with solvents and other chemicals to form a slurry, resulting in the slurry then being coated onto foil, which is rolled to create the cylindrical cell. The electrodes are then dried in very large ovens that are tens of meters long and increase the plant area, energy consumption, and processing time very slowly. And that makes them pretty expensive in tons of different ways. We also need to note that the 4680s Tesla's currently using in the Cybertruck are a hybrid type. The anode is dry coated, but the cathode is not, resulting in the cathode accounting for over 35% of the total cell cost. Tesla still buys from suppliers like LG, where they're coated using the traditional wet process. Producing the cathode with a dry coating is the most challenging part, but it also is the biggest lever to reduce costs. With dry coating, the mixing process is no longer necessary, nor is the substantial energy consumption of the expensive ovens. Using a dry electrode coating process, this means going directly from powder to film. This technique removes the entire step of adding and removing solvents, and it allows Tesla to achieve 10 times reduction in factory footprint and a 10-time reduction in energy consumption, and that's a massive reduction in investment. 2. How did Tesla achieve dry coating for both the anode and the cathode of the 4680 battery? Of course, Tesla couldn't do this alone, so Elon initially acquired Maxwell Technologies. They're a company that's claimed to have invented the dry coating process for manufacturing supercapacitors. But Tesla wasn't interested in supercapacitors. They primarily wanted the rights to the dry coating process to make the 4680 Gen 3 batteries. However, due to some limitations related to production speed, Tesla sold Maxwell, but Elon retained the intellectual property rights related to the dry electrode coating and kept a few teams familiar with this technology. Among them was a world-leading expert in dry electrode manufacturing technology. And ultimately, Tesla had to internalize this process at its own factory. So, was Tesla successful with the dry electrodes? According to revealed sources, Musk asked the battery team to cut costs by the end of the year and develop one of the most important improvements at the time, possibly referring to the dry coating of the cathode. The info cites 3 informants. 2 of these sources also said Elon might abandon battery cells if the issue isn't fixed by the end of the year. But the good news we've received is that a report from China claims that Tesla did finally resolve the dry cathode coating process, paving the way for a major cost reduction for its 4680 cells. This allows the company to make both anodes and cathodes using dry coating technology. The report also states Tesla plans to mass produce and install 4680 cells with dry electrodes for consumer vehicles by the end of the year. year. This info has been cited by people said to be familiar with the matter, and it's also been confirmed by the Chinese publication Late Post. Although this process was perfected in 2022 and proven successful in the lab, scaling it up for production has been a nightmare with dismal yields. According to a report by Late Post, the issue is that the dry-coated cathode rollers kept breaking down because the cathode material is much harder than the anode material. Each breakdown led to 45 days of downtime, contributing to increased costs in Tesla's battery division. The solution was to replace the equipment with better machines, but this required additional expenses that Tesla's management did not approve of at that time. However, Tesla eventually figured out how to produce a battery anode using the dry process. This is crucial because, as mentioned, the cathode part of the battery is usually a lot more costly than the anode. Therefore, producing the cathode using the dry process will significantly cut the production costs of Tesla's 4680 batteries. 3. How will the energy density of the 4680 Gen 3 battery increase? When the Maxwell Technologies acquisition happened, Dr. Maximilian Holland wrote that Tesla's 4680 battery cells cost around $100 a kilowatt hour, but dry cell electrode manufacturing technology is expected to cut the cost of the cells by 10 to 20% compared to traditional wet cell manufacturing techniques. So, if Tesla is as successful as reported, the 4680 batteries are now a lot cheaper, at about $80 a kilowatt hour, close to the price of the cheapest LFP battery cells currently on the market. Dr. Holland also said that with a successful dry electrode process, Tesla's going to save time, and the environmental benefits will also bring significant other benefits, along with some other performance benefits that Maxwell alluded to and Tesla is certainly keen on, because these benefits include energy density hitting 300 watt-hours a kilo compared to 500 watt-hours a kilo instead of 232 to 244 watt-hours per kilogram like the Cybercell has in the current Cybertruck. So, how does the energy density of the 4680 Gen 3 battery go up? It seems Tesla will indeed begin producing the 4680 cells by the end of the year using a dry electrode process that they've been researching for about 3 years now. Those familiar with the matter indicate that Tesla will mass produce and install 4680s with dry electrodes in consumer vehicles by the end of the year. However, the upcoming Gen 3 version of the 4680 will not only feature an improved dry-coated cathode for better efficiency, but the Gen 3 cells may also incorporate new chemical changes. Now, this might not happen at the same time, but another report indicates Tesla's figured out how to produce next-gen 4680s rich in manganese, which lasts a lot longer and has a much higher energy density. Right now, the cathode of the 4680 Tesla cell battery is NMC811 with 81% nickel, 12.4 cobalt, and 6.6 manganese. This means that in the upcoming Gen 3 update, manganese will be prioritized in higher terms. Tesla might have figured out how to make manganese-rich battery cells last longer with doped cathode active material. Manganese-rich cathode active materials like LiMn204 have long been considered an interesting option for their low-cost, high-voltage, and relatively low environmental impact. But they haven't been seriously considered for EVs due to the tendency for rapid degradation. Now Tesla has patented a new doped manganese-rich cathode active material that it claims to have increased the longevity of those battery cells. In the patent application, Tesla says that its doping of the material results in better capacity retention at 50 cycles than regular manganese-rich cathodes. 50 cycles, that's still nowhere enough for electric vehicles, as it would represent about 12,000 miles of driving. That said, 94% capacity retention at 50 cycles, that's still a good sign as degradation often slows down, and therefore, the battery could still have decent retention at much higher cycles. Back in 2022, Elon said in regard to manganese is an alternative to iron and phosphorus for scaling cathode production to several terawatt hours a year. Manganese also requires less lithium and it operates at a higher voltage. However, as far as we know, manganese batteries lose capacity faster, and researchers are trying to make them more durable. You might wonder why Tesla would want to use manganese-doped cathodes in their 4680 Gen 3s despite such a huge drawback. The main reason is that energy density is much more important to Elon in achieving a crazier driving range than what the 4680 Gen 2 is currently offering. Switching to a higher concentration of manganese improves the energy density in the battery cells and increases the driving range without additional cost for Tesla. And that's the main reason why Elon values this. If Tesla can mass produce these new 4680s using both dry anodes and cathodes and increase energy density by using manganese doping, it will make 4680 battery cells truly stand out. This is an exciting development that could lead to the wider use of manganese-rich active cathodes. We'll have to wait and see how powerful the 4680 Gen 3 battery will be with this improved chemistry. So, what has Tesla done to test the 4680 with both dry anode and cathode electrodes? Naturally, they've installed it in the Cybertruck. 4. 4680 Gen 3 battery real-world testing. It's no longer an exaggeration when Tesla, in their second quarter 2024 update letter, along with their second quarter earnings call, Lars Moravi said Tesla had successfully built the first Cybertruck test vehicle with a 4680 Gen 3 battery using the dry cathode manufacturing process at a mass production facility, which is a major milestone. That means Tesla has been able to mass produce 4680 battery cathodes using the dry process, something Maxwell Technologies had previously attempted to do before Tesla took over. But it doesn't stop there. And surprisingly, we also get to see the first real-world dry cathode validation testing of the Cybertruck. Joe Techmeyer, the resident Giga Texas drone operator, recently took to the skies above the factory and noticed a nice black wrapped Cybertruck with a blue logo. Joe made this observation in passing. However, Tesla's head of the 4680 program, Bonnie Eggleston, responded by writing, "Nice shot of the dry cathode Cybertruck." This marks our first look at the dry cathode 4680 Tesla Cybertruck. From the outside, it might look just like another beautifully wrapped Cybertruck, but as we talked about, it's a one-of-a-kind special Cybertruck. When fully ramped up, this Cybertruck will be hundreds of thousands of dollars cheaper to produce than the current Cybertrucks on the roads. This might not seem like a big deal for a $100,000 truck. However, automotive profit, as Elon likes to say, is a game of pennies. There are 100,000 unique parts and processes, and if you can take out a penny cost from every step, you're increasing your profit by thousands of dollars. However, with the dry cathode process, Tesla is able to remove hundreds of dollars from Cybertruck's price by improving upon a single component and process. And that is truly a major advancement because not only is Tesla testing the battery cells in a Cybertruck, but they're also making these cathodes on mass production equipment. That means they've successfully achieved mass production of 4680 cathodes using the dry process, and that significantly cuts manufacturing costs compared to the traditional wet process. Tesla plans to begin mass production of the 4680 batteries with dry process cathodes in Cybertruck by fourth quarter this year, and this will reduce battery production costs, helping Tesla cut their costs lower than its suppliers. More importantly, with a cheaper battery pack, the pickup truck's price will likely go down without compromising performance. And that's great news for those of us looking to own an off-road vehicle this year or next. Current 4680 battery production progress. If there's an automaker known for accelerating production speed and processes globally, it's undoubtedly Tesla. Recently, not only in electric vehicles, but also in the production process of the 4680, Tesla achieved several notable milestones second quarter this year. In their second quarter 2024 update letter, Tesla noted that they were able to make 50% more batteries in second quarter compared to first quarter. 4680 battery production increased dramatically second quarter, resulting in 51% higher sales than first quarter, while significantly reducing the cost of goods sold. Tesla's now making over 1,400 4680 cell Cybertrucks a week. But that's not the end of the line, as Tesla will continue to ramp up until costs are at our cost parity target by year end. In summary, Tesla's doing very well in ramping up the production of 4680 batteries and addressing significant technical issues. We think 2025 is going to be a breakthrough year for Tesla's 4680 battery production, and their engineers will be able to focus more on improving performance and energy density of the batteries in the future. This is important and extremely exciting. Once the production of 4680 cells gets stepped up, it's no longer going to be a surprise if dry electrode batteries will also be deployed for other new models of the company. Manganese can likely be used with a small amount of nickel and cobalt. There will be less nickel and cobalt in this new Gen 3 4680 battery. Elon Musk is not just focusing on developing a battery with higher energy density for long-range vehicles. His goal is to provide a lower-cost battery that still delivers the same performance. The demand for lithium and nickel is very high, while the demand for manganese, not as much. Incorporating manganese batteries into production will help cut battery manufacturing costs. Research on batteries will continue and may never stop. If Tesla can reduce battery costs by a couple $1,000s and surpass LFP batteries in cycle life, then manganese battery chemistry is going to be very meaningful. There was a recent report from Reuters or another source saying LG will beat Tesla in producing dry electrode cells, meaning that making 4680 cells using the same dry electrode process as Tesla. However, this is unlikely and just typical misinformation about Tesla, as that's not expected to happen until 2026 or 27 at the earliest. It seems Tesla will actually begin producing 4680 cells using the dry electrode process they've been researching about for the last 3 years by the end of this year. The dry electrode process for the cathode is considered the most challenging part of the 4680 battery cell and the highest cost component, accounting for over 35% of the total cell cost. Therefore, we need to emphasize again how significant it is that Tesla can cut the cost of 4680 cells by around 30% while also improving energy density throughout the dry cathode. Truly a game changer for Tesla. Of course, there's always going to be minor issues that come up during large-scale production, especially in early stages, but it's clear Tesla's going to ramp up very quickly. Moreover, it seems they have a scalable process for producing the Gen 3 4680s for the next generation of electric vehicles. This is also significant because Tesla has years of experience, not only from their own efforts, but also from the technology they got from Maxwell Tech. Therefore, the Tesla team is confident that they have a scalable process by early 2025, and that also gives us lots of confidence. Tesla's success with 4680 Gen 3 is a major leap forward, demonstrating their battery technology should never be underestimated. They are improving day by day, month by month on every production line. The 4680 battery stands out more than Toyota's solid-state batteries, which have been heavily hyped. While the 4680s made real-world progress, Toyota's solid-state batteries are increasingly becoming more mythical. This achievement not only affirms Tesla's superiority in battery technology, but also lays a solid foundation for future advancements in the future. So, what do you think about the new success of Tesla's 4680 next-gen battery? Let us know in the comments below. Tesla has identified and resolved the bottleneck issue in the 4680 battery production, aiming to reduce production costs by up to 20% compared to current suppliers. The 4680 battery, get this, has the capability to support over 1,000 Cybertrucks every week, and that hits 50% growth and it cuts wait times. If this is successful, 4680 batteries are going to become the lowest cost domestically produced battery in the States. How has Tesla addressed the 4680 battery issue to create a significant shock industry-wide? What challenges is the 4680 battery facing at the moment? Earlier, Tesla's 4680 faced significant criticism, partly due to Tesla's bold claims. They had acquired dry cathode technology from Maxwell Technologies for nearly $320 million. Initially, the technology didn't work, meaning that Tesla spent years trying to make it work. However, they eventually attained success a couple weeks back, or around a month ago. Media reports suggested that LG Chem had beaten Tesla out in dry cathode production, but I don't recall whether it was either LG Chem, maybe it was Panasonic, or it could have been Samsung. Reading the news, we found it pretty funny because LG Chem, Samsung, and Panasonic have not yet started making those dry cathode batteries. Media likes to report inaccurately. Fake news, anyone? So you can't really rely on them to get the full scoop. Currently, in the Cybertruck, the battery energy density is at 256 watt-hours a kg, and that's a big-time improvement over the first-generation battery, but still lower than the estimated density of Panasonic's 2170 that's being used right now in Tesla's Model Y. The previously mentioned 54% range increase is directly related to the improvement in energy density, not only at the cell level but also at the pack level. Specifically, 40% of this increase comes from improvements in the battery's energy density. The remaining 14% relates to the integration of the cells into the vehicle. Although 2170 battery technology has improved since 2019, we think that Tesla's got the potential to hit around 300 watt-hours a kilogram for the next generation of batteries. One major way Tesla could achieve this is by incorporating more silicon into the battery's anode. Tesla recently filed a patent related to enhancing the 4680 by adding silicon to the anode, although silicon could cause issues with expansion and cracking the anode material. This could lead to faster charging and higher energy density, but might impact battery longevity. Some new tech, such as the highly elastic binders and new electrode designs, could help address this issue. According to a report by James Ma on X, the second-gen 4680 battery in Model Y has a small amount of silicon in the anode, and that shows an improvement from the first-generation battery. Some Model Y vehicles made in Austin still feature the 4680 battery, though with changes in the cathode chemistry and anode, the Gen 2 version of 4680 battery uses NCMA chemistry with a composition of 82% nickel, 11% cobalt, 5% manganese, 3% aluminum, whereas Gen 1 did have higher nickel and aluminum content and lower cobalt. The battery's anode is made using natural materials with a bit of silicon similar to Gen 1 to enhance battery performance by increasing safety and improving overall efficiency. If Gen 2 had significantly improved over Gen 1, this full version will be even better. In fact, Tesla has not yet begun producing 4680 batteries with dry cathodes. They produced and tested these cells for about a week on the Cybertruck. The company has initiated testing of their vehicle with 4680 batteries featuring dry cathodes. Cybertruck's battery cells indeed contain a small amount of silicon in their anodes, and Tesla has mentioned the potential to increase the battery range by 20% due to the integration of silicon in the 4680 battery anode. This could be a major breakthrough if Tesla's predictions come true. A recent Tesla patent describes the method for multi-layer electrode films, where the main issue is the poor adhesion of the active material layer, like graphite, to the metal foil, leading to electrical loss and reduced storage capacity. Silicon, despite its high energy density, encounters issues with volumetric expansion during battery cycles, and that makes it challenging to get that long-term performance. This patent proposes a multi-layer approach, with a silicon-rich layer in the middle and higher adhesion layers on the top and bottom to maintain the stability of the active electrode structure, and that improves connectivity and minimizes separation inside the battery. However, traditional wet processes do not support the multi-layer design as easily as Tesla's dry process. Wet film formation processes, including spraying, slot die coating, extrusion, and printing, can limit the ability to combine active layers and face challenges in achieving uniform material dispersion. Additionally, wet processes are often costly and require time-consuming drying steps, and that can be problematic as the electrode film gets thicker, leading to limitations in the thickness of films produced using wet processes. How has Tesla thoroughly resolved the issues with the 4680 battery? Reports have come out that Tesla's new dry electrode process has finally resolved the issue and could increase the energy density of the 4680. According to sources over in China, if energy density increases by 20%, the 4680 battery becomes the highest energy density battery worldwide and could be produced at scale. Currently, dry cathode technology is not available to automakers, but this means Tesla's production costs for Cybertruck are going to go down and its range will go up substantially. Tesla has finally addressed the issue with a 4680 battery that they face with dry cathode technology. So, what does all this mean? Tesla introduced the first dry cathode for the Cybertruck in July and began testing vehicles with their self-produced 4680 dry cathode batteries. This is a big-time milestone in improving technology and cost efficiency. However, we do remain surprised that it took longer than expected. We don't understand why it actually took years to complete. This means that the battery will be much cheaper for Tesla to make. The major difference between dry and wet cathodes is production cost. And we know you're curious about why dry cathode technology is important for Tesla's batteries. First, let's consider the production costs. Traditional wet cathode technology requires the use of organic solvents such as NMP during production. After the cathode materials are mixed with the solvent, the mixture must undergo a drying process in large ovens to remove the solvent before the cathode layers are cut and then rolled. This process is energy-intensive and costly, with solvent and drying costs estimated to account for about 5 to 15% of the total production cost of lithium-ion batteries. In contrast, the dry cathode technology being developed by Tesla and other companies eliminates the need for solvents in drying processes. The cathode materials are directly mixed into a dry powder layer, which is then pressed and rolled without drying, significantly cutting production costs by up to 20 to 30% compared to traditional wet cathode technology. In addition to cost reduction, dry cathode technology has the potential to improve production efficiency. By eliminating the drying process, production time gets shortened when that speeds up manufacturing. This is particularly important for Tesla as the company scales up 4680 battery production to meet the growing demand. Moreover, removing NMP solvents not only saves costs, but also improves the air quality in the factory and reduces waste disposal costs, as NMP is a hazardous substance that has to be handled carefully. The use of NMP in wet cathode technology is not only expensive but also has negative environmental impacts. NMP is an air and water pollutant, requiring pollution control and waste disposal measures, which adds to the cost and environmental impact. On the other hand, dry cathode technology, by eliminating the need for solvents and drying processes, significantly cuts carbon emissions and energy consumption in battery production. This aligns with Tesla's goal of reducing the environmental impact in its products and production processes. In practice, when Tesla acquired Maxwell Technologies back in 2019, a company specializing in dry electrode technology, it demonstrated Tesla's serious commitment to developing and implementing this technology. Elon mentioned that adopting dry cathode technology is a key part of Tesla's strategy to make cheaper and higher capacity batteries for its EVs. While Tesla's electric trucks are currently being delivered, they don't feature dry cathodes. These batteries are not inferior products, but they are more expensive for Tesla to make. A report from a Chinese publication indicates that the 4680 batteries used in Cybertruck's production currently have a cathode produced using Tesla's dry electrode process and then an anode sourced from a supplier. This means Tesla no longer has to buy anodes from suppliers but can make them using their own dry electrode process, and that significantly cuts down on production costs. It's estimated that those production costs will decrease by around 10 to 15%, which, while not substantial, is still something. If Tesla can incorporate more manganese or silicon into their batteries, energy density will increase. Reports from sources familiar with the issue indicate that Tesla is aiming to start mass production of complete 4680 batteries by the end of the year, with both anode and cathode produced using the dry electrode process. This could increase energy density, although the exact amount is yet to be determined. Some sources suggest this could increase the energy density of the 4680 battery by 20%. If that's true, Tesla could improve the range of Cybertruck to around 400 miles, and that's a game changer. This means Tesla could use a much smaller battery pack than its competitors while still achieving the same range, reducing cost per vehicle and maintaining a significant advantage in electric vehicle production. Stay tuned and see if this holds true, and let me know what you think in the comments. What is the impact of reducing the production costs of the 4680 battery on Tesla vehicle prices? Reducing the production cost of the 4680 could have profound impacts on Tesla's vehicle pricing and the company's financial performance. 4680 is an advanced battery technology that Tesla's adopting to improve performance and reduce the cost of electric vehicle production. In the context of increasing competition in the EV industry, lowering battery production costs could offer significant benefits to Tesla, not only in terms of pricing, but also in competitiveness and profitability. First, reducing the cost of making 4680 batteries could lead to a decrease in the retail price of Tesla models. Yes, please. According to projections, if battery production costs are cut by 30% from 100 kilowatt hours to $70 a kilowatt hour, each vehicle using a 100 kilowatt hour battery could save around $3,000 just from the reduction in battery costs. Given that batteries account for 30 to 40% of the total cost of making an EV, this cut could lower the overall production cost of a vehicle by up to 10%. This means the production cost of a Tesla Model 3 could go down from about $35,000 to $30,000, and that's equating to a savings of about $5,000 a vehicle. Reducing battery production costs could also enable Tesla to lower the retail price of its vehicles, making its models more attractive to consumers. If Tesla does indeed decide to reduce the price of the Model 3 from its current level of $39,900 to about $34,490, this could not only attract more customers, but also potentially increase sales by 15 to 25%. A lower retail price could create a positive shock in the market, helping Tesla expand its market share and strengthen its presence in the mid-range electric vehicle segment. On the other hand, if Tesla chooses not to alter the retail price and keeps vehicle prices as they are, cutting production costs could also provide other benefits. The savings from reduced battery costs could enhance the profit margin on each vehicle, giving the company additional capital to invest in research and development of new technologies. Tesla could use the savings to expand production lines, research new battery technologies, or develop new vehicle models. This could help the company maintain its competitive edge and lead the electric vehicle industry. Overall, reducing the production cost of the 4680 battery could provide multiple benefits for Tesla. First is the potential to lower the retail price of vehicles, making them more attractive and boosting sales. Second is the increased profit margin per vehicle if retail prices stay unchanged, allowing the company to invest further in technology and product development. These impacts could not only improve Tesla's financial performance, but also strengthen the company's competitive position in the EV industry, providing long-term benefits for both the company and us consumers. What improvements have been made at Tesla's 4680 battery manufacturing plants? Tesla's approach to boosting 4680 cell production involves a multifaceted strategy focusing on significantly expanding gigafactory facilities and optimizing the production process. This comprehensive effort is evident through the development and expansion of key production sites, notably Gigafactory Texas and Gigafactory Berlin, as well as the implementation of advanced technologies to streamline the process. Tesla's expanded its Gigafactory facilities to enhance 4680 cell production. Gigafactory Texas, the cornerstone of this expansion, spans approximately 2,500 acres, making it one of Tesla's biggest and most advanced production sites. The facility is designed with a vast production area of about 10 million square feet, featuring numerous production lines dedicated exclusively to 4680 cells. The site represents a major step forward in increasing production capacity and includes advanced automation and robotic systems to streamline the production process. By early 2024, Gigafactory Texas is expected to achieve an impressive annual production capacity of 100 gigawatt-hours for 4680 cells. Recent upgrades include the installation of high-speed electrode coating machines, which help accelerate production speed and consistency, reduce production time, and improve overall efficiency. Regarding Gigafactory Berlin, this facility is strategically positioned to serve the European market and is equipped with advanced manufacturing technologies. By the end of 2024, Gigafactory Berlin aims to produce 50 gigawatt-hours of 4680 cells annually. This ambitious goal reflects Tesla's commitment to meeting the increasing demand for high-performance batteries in Europe. The factory combines advanced European manufacturing standards and is equipped with automated systems to ensure high-quality production. Tesla's focus on optimizing the production process is a crucial component in boosting 4680 cell output. Data analysis and AI play a key role in this optimization effort. Data analysis is vital for monitoring and refining the production process. By tracking machine performance, raw material quality, and production line efficiency, Tesla can identify bottlenecks, anticipate potential issues, and implement corrective measures quickly. Predictive maintenance, driven by historical data and real-time metrics, helps minimize downtime and ensures continuous production. This proactive approach allows Tesla to address problems before they escalate, maintain smooth operations, and reduce production disruptions. Quality control is another important area where data analysis contributes to optimization. Advanced data analysis enables early detection of defects and ensures high standards for cell quality. By analyzing data from various production stages, Tesla can identify patterns and anomalies that may indicate quality issues. This allows for timely adjustments and improvements, ensuring that the final product meets the company's rigorous quality standards. AI further enhances production optimization by improving scheduling, inventory management, and streamlining supply chain operations. Machine learning models play a crucial role in refining the production process and enhancing overall efficiency. AI-driven automation handles tasks such as cell assembly and testing with high precision and speed, reducing human error and increasing production throughput. Additionally, AI supports supply chain management by forecasting demand and optimizing inventory levels. This helps prevent delays, reduce costs, and ensure that production lines have the necessary materials and components for smooth operation. Despite significant progress, Tesla faces several challenges in boosting 4680 cell production. One major one is managing the supply chain for specialized raw materials used in battery production. To address this, Tesla's formed strategic partnerships and invested in raw material processing facilities. These efforts aim to ensure a stable supply of critical materials and reduce reliance on external sources. Maintaining high-quality standards is another challenge that Tesla addresses through ongoing technological improvements. Advances in electrode materials and battery chemistries play a huge role in driving 4680 battery technology forward. For example, improvements in electrode materials and electrolytes contribute to enhancing performance. Imagine a battery that slashes production costs by half and shrinks the number of cells needed from 4,400 to only 960. By eliminating traditional tabs and optimizing electron flow, this isn't just an upgrade, it's a game changer that could redefine the future of electric cars. What makes Tesla's 4680 dry cathode battery a breakthrough in EV technology? What makes Tesla's 4680 dry cathode battery different? Tesla is currently using 4680 cells to produce structural battery packs for the Model Y. However, these vehicles have encountered issues with poor charging performance and low energy density, leading to their swift removal from the sales catalog. The large size of the 4680 cells makes cooling difficult, limiting the battery's performance. These problems have become apparent, and Tesla recognizes the need for immediate improvements. A key factor in the improvement is the dry process. The dry process, dry battery electrode (DBE), is fundamentally different from the wet process, wet battery electrode (WBE), currently in use. The dry process eliminates hazardous solvents and oven firing processes, saving time and space, and is more environmentally friendly. Specifically, the dry process is used to produce the anodes of the battery, the conductive electrodes at the edges of the cell, rather than the wet process previously used. Tesla's 4680 cell suppliers, including LG and Panasonic, are working to reduce costs and increase the production of 4680 cells. If Tesla can effectively scale the dry anode method, the production of 4680 cells in battery packs will become cheaper and more efficient. So, what makes Tesla's dry cathode 4680 battery different? We'll give you a clear analysis here. First, the tabless design. Have you heard about this? The tabless design of the 4680 also impacts the manufacturing process and ease of production. Think of tabs as small knobs on the top of a regular battery cell. The absence of tabs means that the cell body production process does not need to pause to add tabs, reducing the likelihood of errors by eliminating a step and allowing for a quicker startup. The tabless design of Tesla's dry cathode 4680 battery is one of the significant and appreciated technological breakthroughs, enhancing performance and reducing production costs. In conventional lithium-ion cells, metal tabs connected to the electrodes outside of the battery, and that enables current flow. However, these tabs can cause serious issues like increased temperature at the connection points, leading to reduced battery lifespan or even failures. Studies show that hotspots can raise the battery temp by up to 20 degrees Celsius during a fast charge-discharge cycle. Additionally, attaching tabs to electrodes in a complex process that slows down production speed and increases costs. Tesla estimates that removing the tabs could accelerate production speed by about 20% thanks to the reduction of this complex step. Furthermore, tabs concentrate current at specific points on the electrode, causing uneven current distribution, and that reduces the overall performance of the battery and can lead to overheating. Tesla's choice of a tabless design addresses these issues by completely eliminating traditional metal tabs. Instead, the electrodes are connected directly to the battery's end through multiple small contact points along the edge of the electrodes. As a result, the battery operates at a more stable temperature, extending the battery's life, with the average operating temperature reduced by about 10% compared to regular tab designs. At the same time, the battery manufacturing process becomes simpler, which speeds up production and reduces costs. Tesla forecasts that the tabless design could cut the production cost per kilowatt hour of the 4680 battery to under $70 compared to the $100 to $150 kilowatt hour of traditional batteries. Furthermore, with a less complex manufacturing process, the startup time for a new battery production is faster, allowing Tesla to be more flexible in responding to market demand. Now, not only does the tabless design improve durability and performance, but it also contributes to the increased energy density of the battery. With the space saved by eliminating tabs, Tesla can integrate more active material into each cell, resulting in higher energy density. According to Tesla, the 4680 with a tabless design can get an energy density that's 5 to 10% higher than that of traditional tab cells. This means that a battery pack of the same size can provide a longer driving range for electric vehicles or reduce the number of cells needed, thereby lowering the overall weight of the vehicle. The second difference, removing tabs. Why did Tesla decide to remove tabs from their batteries? Removing tabs in the battery design not only improves durability and overall performance, but also plays a crucial role in optimizing the distance electrons need to travel inside the battery. This directly impacts the battery's charge-discharge performance and its ability to deliver more energy efficiently. Eliminating tabs also shortens the distance electrons need to travel in and out of the battery, meaning less resistance and less energy loss during this process, which enhances the overall efficiency of Tesla vehicles. Experts suggest that in a tab design, the distance electrons must travel from distant regions of the electrode to the tab can be several centimeters, depending on the battery size. For example, in a cylindrical cell with a diameter of 18 millimeters, the travel distance can be up to 9 millimeters from the center of the electrode to the tab. This distance creates resistance differences on the electrode surface, leading to energy loss as heat, causing overheating and affecting the battery's lifespan. By removing the tabs in the 4680 battery design, Tesla has reduced the distance the electrons need to travel. Instead of going to the central point, electrons can pass through multiple connection points along the edge of the electrode, shortening the travel distance to just a few millimeters or even less depending on the location of the contact points. In regular lithium-ion batteries, tabs are metal strips connecting the battery terminals to the external circuit. They concentrate current from the electrodes, positive and negative, and conduct it out of or inside the battery during charging and discharging. However, due to this layout, electrons have to go a long distance from far points on the electrode surface to the tab, and that results in energy loss as heat has reduced electrical transmission efficiency. This change shows that Tesla is really committed to accelerating the improvement of their battery technology. The benefits of the shorter travel distance are evident in this change. As the distance electrons must travel is reduced, the internal resistance of the battery also goes down. Tesla estimates that the tabless design could lower the internal resistance of the battery by 5 to 10%, depending on the size and configuration of the battery. This helps minimize energy loss as heat, improves charge-discharge performance, and extends the battery's lifespan. The distribution of current within the battery becomes more uniform. This improves electrical transmission efficiency, meaning more energy from the battery is converted into mechanical energy for the electric vehicle, rather than getting lost as heat. According to Tesla, reducing the electron travel distance can enhance the battery's energy efficiency by up to 5% compared to tab designs. Additionally, the tabless design accelerates charging for Tesla vehicles. With shorter travel distances and lower internal resistance, the tabless battery can charge faster and discharge more powerfully. This not only cuts charging time, but also improves the ability to deliver high current over short periods, and that's crucial for EV performance. Tesla forecasts that the tabless design could increase fast charging speeds by 10 to 15%, allowing vehicles using the 4680 battery to fully charge in less than 15 minutes. How do the structural advantages of the 4680 cell contribute to reducing vehicle production costs? Okay, so Tesla's new 4680 cell manufacturing process gives several advantages over the traditional wet process, particularly when we're talking about cost. It's estimated that the dry process can reduce total costs by up to half. This savings primarily comes from cutting expensive solvents and the energy-intensive drying process that's used in the wet method. Specifically, the solvent NMP used in the wet process requires recycling or disposal, significantly increasing production costs. The dry process removes these steps, substantially reducing material and energy costs. In addition to cost benefits, the dry process also increases production speed and is related to environmental protection. The dry process not only helps lower costs, but also accelerates production. By eliminating steps like drying and solvent recycling, the 4680 cell manufacturing process is a lot faster, and that allows Tesla to up their output without expanding their factory scale. Moreover, the dry process is more environmentally friendly, cutting the emission of hazardous chemicals and saving energy, thereby contributing to a lower environmental impact when making batteries. Are you curious about the reasons for switching from the 2170 to the 4680 cell? Well, Tesla's transition from the standard 2170 cell to the 4680 cell is driven not only by technical reasons, but also by economic benefits. One of the big advantages of the 4680 is its smaller size that allows it to serve as a structural support for the vehicle. This means that not only does it save costs in producing the 4680 cells, but also reduces the overall manufacturing costs for the whole vehicle. Technical analyses suggest that the 4680 can cut the number of cells needed in a battery pack, thereby decreasing the associated costs of cell interconnections and management, while also improving material efficiency. Tesla has claimed that the 4680 cell can help reduce the cost per kilowatt hour of energy by about 14%, while improving energy density by an additional 16% compared to the 2170 cell. These figures highlight not only the potential for cost savings, but also improvements in performance, making the 4680 cell an optimal choice for new models like the Cybertruck and Model Y. The ease and cost effectiveness of the 4680 cell can offer advantages over the 2170 for Tesla. The 4680 has a major manufacturing advantage due to its larger size compared to the 2170. The 2170 sure is tall and thin, but the 4680 is wider and more robust, and that makes making them easier. The larger size of the 4680 allows for a reduction in the number of cells needed for each battery pack, thereby reducing the steps involved in assembling and connecting cells. Specifically, a battery pack that contains 4,400 2170s only requires 960 4680s to achieve the same energy level. This not only reduces production time, but also significantly lowers material and manufacturing costs. Moreover, using the 4680 cell allows Tesla to optimize space and increase energy density in the battery pack. With the number of cells needed to reduce from 4,400 to 960, Tesla can substantially cut down on the amount of material required to encase each individual cell. This not only saves space, but also allows Tesla to design a battery pack with a higher energy density, making the space occupied by the battery pack more efficient. The reduction in battery volume improves overall vehicle performance, particularly in high-power models like Cybertruck. All these improvements could lead to a reduction in vehicle production costs, particularly for those high-end models like the Cybertruck. Tesla plans to make approximately 250,000 Cybertrucks annually, and to get this target, they'll need a large number of 4680 battery packs. The easier production process and lower cost of the 4680 cells will not only help Tesla hit their production goals, but also allow them to lower the price of Cybertruck, and that makes it more attractive to us consumers. What strategy does Tesla have to optimize 4680 battery production in the final months of the year? According to a report by Chinese Late Post, citing internal sources, Elon aims to produce the first mass-produced 4680 cells with dry-coated electrodes before the end of the year and use them in customer vehicles. If this does prove effective, Tesla may abandon the 4680. Late Post reports that the 4680s currently installed in the Cybertruck are a hybrid type. The anode's been dry-coated, but the cathode has not. Tesla still sources them from suppliers like LG, where they're coated using the traditional wet process. Making the cathode with a dry coating is the most challenging part, but also the biggest leverage for reducing costs. There are also reports that Tesla succeeded in developing a high manganese cathode, increasing capacity by about 16% compared to current cells. High manganese cathodes are cheaper than high nickel materials, for instance, but their cycle stability is still too low to consider for EV use. The manganese-rich doped cathode materials for which Tesla has filed a patent could extend the lifespan of such batteries. Elon and the Tesla team have discussed using doped manganese cathodes, such as lithium manganese 204, to enhance battery energy density. However, a challenge is that these batteries may degrade more quickly, which is one reason Tesla has not yet scaled them up for mass production. However, 94% of the initial capacity has been retained after 50 cycles. While this is better than the previous manganese battery chemistries, it's still a lot lower than the level needed for EVs. Tesla model vehicles using the 4680 cells perform pretty well, as they can extend the range by about 50 miles at a cost of $1,600. Clearly, Tesla's found ways to optimize the range of these battery packs, as we all predicted. Although mass production may not start until 2026 or 2027, recent information indicates that Tesla plans to install 4680s with dry-coated electrodes in vehicles before the end of this year. The new version of the 4680 cell is expected to be more efficient and may feature different chemistry, although this might not happen at the same time. What motivates Tesla to prioritize internal battery upgrades over purchasing from established battery manufacturers? One of the notable factors in Tesla's approach to developing battery technology, particularly the 4680 battery. While many of Tesla's competitors like GM, Volkswagen, and other automakers rely on external suppliers for their electric vehicle batteries, Tesla's chosen the path of developing and manufacturing their own batteries. This decision not only reflects Tesla's long-term strategy, but also gives several competitive advantages, helping Tesla maintain its leading position in the global electric vehicle market. Many of Tesla's competitors, like GM and Volkswagen, have opted to partner with major battery suppliers like LG Chem, Panasonic, and CATL to ensure a stable supply of batteries for their electric vehicle lines. This strategy allows these companies to quickly bring EV models to market without investing heavily on internal battery technology research and development. For instance, VW has announced plans to build 6 battery production plants in Europe with a capacity of up to 240 gigawatt-hours by 2030. On the other hand, GM, they've announced plans to build 2 battery manufacturing plants in the US with LG Chem, aiming for a capacity of 70 gigawatt-hours by the end of the decade. While this strategy helps Tesla's competitors easily access existing battery technologies, it also has certain limitations. They need to purchase batteries from external suppliers, making it challenging for these automakers to optimize production costs and maximize profits. Battery prices, which account for about 30 to 40% of the total cost of an EV, are often dependent on suppliers and can fluctuate based on the availability of raw materials. Relying on suppliers also reduces automakers' control over battery quality and performance, which can impact the performance and reliability of their vehicle. The advantages of Tesla's strategy for internal battery development are clear. In contrast to the competition, Tesla's chosen to develop and manufacture their own batteries, exemplified by the development of the 4680 battery. This decision provides Tesla with significant competitive advantages. The 4680 offers 5 times the energy and 6 times the power of the previous 2170. Furthermore, the production cost of the 4680 is expected to go down by 56% due to its tabless design and dry cathode technology. These improvements not only help Tesla reduce their vehicle costs, but also enhance its competitive pricing in the market. Tesla also benefits from its control over the battery supply chain. Amid global material shortages and supply chain disruptions caused by the pandemic, Tesla's demonstrated its ability to adapt flexibly by fully controlling its battery production process. This allows Tesla to avoid supply chain risks and ensure they have sufficient batteries to meet the increasing demand for EVs. For example, in fourth quarter of 2022, Tesla delivered over 400,000 vehicles, capturing more than 20% of the global market, while many competitors faced battery shortages and disrupted production. While competitors like GM and Volkswagen rely on external suppliers for batteries, Tesla's leveraged its internal production capabilities to optimize costs. It's estimated that Tesla could save billions of dollars in battery costs as it scales up 4680 production. This helps Tesla maintain higher profitability and potentially lower vehicle prices, thereby continuing to expand its market share. Right now, Tesla's Model 3 has become the best-selling EV in the world, over 1.3 million units sold by the end of last year, largely thanks to the cost and performance advantages of their 4680 battery. We hope you'll experience the utmost relaxation after watching this video. If you did, hit that like button and join your Tesla Car World community by subscribing to the channel. Be sure to hit the notification bell icon and stay tuned for any fantastic videos coming your way. Your feedback and time are always appreciated, and we look forward to seeing you soon. Take care and God bless. Bye.